Hey everyone, I'm going to do a quick overview of the slides from chapter 2. This is on the chemistry of life. So I'm going to share my screen with you. These slides you can access on Canvas, and I've just popped this out into the Google Slides. All right, so this is all chapter 2. This is the chemistry of life. And the first part of this, or these sets of slides, is about water. So let's talk through some of these slides here, and I'll add a couple of drawings on here too for a few of the slides. So water is one of the most important things. If we had been in the classroom, we would be talking through chapter 1 first, which is all about understanding what science is, but also just understanding the basic concepts of biological sciences. And one thing that we talk about in chapter 1 in Introduction to Biology is the characteristics of all living things. So what do living things share, and how do we define life? And one of the nice things for you to do is just to kind of brainstorm what living things require, or what kind of makes up shared characteristics of living things. And one of the interesting things that you'll find, you might not even think about it, is that water is required for life. I mean, you know this because you hear in the news about looking for other planets, right? So our NASA Space Discovery Center is always looking for the possibility of life on other planets, and the key thing that they're looking for is the existence of water. Because for our planet, at least, and for our understanding of how living things work, we know that water is an absolute necessity, that life cannot exist without water. So we're going to spend a little bit of time just talking through the characteristics of water and why water is such an important and very unique thing, molecule, that makes up such a significant part of living things on our planet. So I'm sure you remember what water looks like from your basic chemistry classes back in junior high or high school, or if you've taken chemistry here already at Los Rios or other community colleges, you've seen the molecular makeup of a water molecule. This picture here is showing you sort of a cartoon image of what water molecules might look like when they are in suspension. And you can already kind of guess as to what state of matter these water molecules are in, right? States of matter, if you recall, and let me, let's see. I don't usually use Google Slides, so give me a second. I'm going to see if I can add on. Oops. Sorry, I'm seeing if I can add on if I can draw on my slides. It looks like I cannot draw on my slides. Well, that's kind of cool. Let's see what happens when I do this. Aha. Okay, so I can point, but I can't draw, but that's okay. All right, so let's look at these water molecules. So water exists as an oxygen atom. So these large red circles here represent oxygen, and they're drawn as these very large things because not because oxygen physically takes up a lot of space, but energetically it does, right? It has many electrons on it. It has 8 electrons and 8 protons and neutrons on its nucleus, and so those orbiting electrons kind of create this large energy field around them, versus the 2 hydrogen atoms here in blue that are bound to oxygen. These guys only have 1 electron each, so they exist in a much smaller energy state, so they're drawn a little bit smaller too. And notice we call this polarity of a water molecule. If you think about what a pole is, like we know North Pole versus South Pole, right? The opposite extremes. If you know anything about magnetism, that's also a positively charged or positive pole and a negative pole. So polarity has to do with this kind of opposite linearity to something, or where you have a positive and negative end, or an opposite pole, one side to the other. And so when we're talking about polarity with molecules, it really has to do with the state of energy of the molecule, or the orientation of these energy fields, essentially. So oxygen is a really high energy rich molecule. And it's strongly negatively charged because it has these electrons in its outer orbital that actually kind of require balancing. That's where protons, or these hydrogen atoms come in, and I can draw that for you in just a bit. But because of the nature of these positively charged hydrogen atoms and this kind of negatively charged oxygen molecule, these guys sort of polarize, which means that the oxygen, this big energy-rich electron-rich atom, sort of has this electrical charge out here in a negative sense, and these guys sort of exist in a positively sense charged nature. So it creates this negative end here and a positive end here. And this is all sort of, these aren't true charges, they're not ionic charges, which we'll talk about in just a minute. So let's continue to work through this. But you can see that all of these water molecules sort of exist in this polar state where you have this sort of large red part here, which is essentially the negatively charged end, and these little blue guys here, which are essentially the positively charged ends. And you'll see that how these water molecules kind of exist with one another is that they sort of align themselves so that the blue and the red ends kind of connect. And you'll always sort of see this, that for a water molecule sitting next to another one, you'll always see this sort of polarity and this kind of organization where the positively charged protons sort of align with and connect loosely with a hydrogen bond with these oxygen atoms there. So as I was stating, you can kind of look at this and decide the state of matter. Matter would be, right, existing in a gaseous form or liquid form or a solid form. And the closer together the molecules are in the presence of each other, will help determine what state we're looking at. So you see that there's quite a bit of distance here still between these, but they're not crazy spread apart. So I would guess that we're looking at a liquid form of water here instead of the gaseous form, which would be like water vapor, or the solid form, which would be ice. Okay, a little bit more on this polarity concept, right? So if you look at water again, water is oxygen and 2 hydrogen atoms. So the oxygen is this energy rich. It has roughly negative charged end to it. And these hydrogen atoms have a roughly positively charged end to it. So when you have a lot of water molecules kind of sitting next to each other, you'll see that they polarize, they align themselves so that the oxygen end roughly associates or forms what we call a hydrogen bond, which is this loose association between this negatively charged region and this positively charged region of an adjacent molecule. So you see all these yellow connections here in this picture are showing you the negatively charged oxygen binding to a neighboring positively charged hydrogen molecule or hydrogen atom with the next water molecule. So there is some level of association, and the closer together these molecules get, in other words, when they form ice or solid state of water, then this link becomes much more crystallized. So it's a crystallization of this stuff, and they become much more organized as they get closer together. So I keep using these terms element, or I use these terms atom or molecule. So let's really break down what we're talking about here. When we're talking about elements, right? An element is exactly what's defined here, a pure form of matter that cannot be broken down into anything else by normal physical means. So when we're talking about elements, we can refer to the periodic table of elements. This is what scientists have discovered so far on our planet, and there are more elements being discovered almost on a regular basis, but so far, this is what is known to be in existence, at least on our planet. So we have different regions of our periodic table of element that actually signify different characteristics of these elements. And again, what we're looking at here are things that can't be broken down into anything smaller than as they exist. And you can look at this and say, well, this is oxygen here. Oxygen is an element, and you can have an atom, a single atom of the element oxygen, right? So using these terms, sort of understanding the difference between what we're talking about. An element is just this thing, whatever we're looking at, a non-metal or a metal element. And an individual one of these elements would be an individual atom. And these atoms can get together with other atoms of the same kind. Like, for example, the oxygen that we breathe is 2 oxygens put together. 2 oxygen atoms put together to form a molecule. So a molecule is a combination of 2 or more atoms. It could be of the same element or of different elements. What we just looked at was water. Water is 1 atom of the oxygen element and 2 atoms of the hydrogen element to make a molecule of H2O. So 2 hydrogens and 1 oxygen, H2O or water. right? So elements are like what it is we're talking about, the characteristics of the element sort of define what it is we're working with. A single piece of that element would be a single atom. Atoms can get together with other atoms of the same element or of different elements to form molecules. And then molecules can be compounded to make compounds, right? So to make large macromolecules or compounds. And all of these elements have different types of reactivity. So their ability to get together with each other is based on their reactivity, how reactive they are. And that's actually due to how many electrons they have in their outer orbital. These guys over here, if you've taken a chemistry course, you might remember this stuff. So we have our noble gases over here in this very far right part of our periodic table of elements. These guys are noble gases. They have all of their electron orbitals filled completely in the outer part of their state of existence. And so they are actually rather stable. They don't react really with anything else. And then as you sort of move into this periodic table of elements, now we have some highly reactive elements as we move closer and closer sort of towards the inside. And I think I'm going to take just a second and let's just look at this for a minute. And like, what am I talking about with all of these things, these elements and the electron orbitals? So electrons sort of exist in these fields of energy in concentric rings outside of the nucleus of an atom. And that's actually not really true, but that's how we're going to focus on it. If you take an advanced chemistry course, you'll start to understand that there are different ways that these electrons sort of go into orbit around their nucleus. That are a lot more complex than just looking at these as concentric rings, but we'll just sort of focus on it like this. So the organization of these electron orbitals is actually rather systematic. So there's a rhyme or reason, there's an understanding we have to how electrons sort of place themselves in orbit around their central nucleus. So to describe what I'm talking about, this is an atom that we're looking at. This is a picture of an atom. An atom has two major kind of parts to it, right? It has the center part that is the nucleus, and the nucleus is composed of positively charged protons and neutrally charged or no charged neutrons. And the number of protons inside the nucleus is usually equal to the number of electrons outside in orbit around that nucleus. That's not always true, but almost always true. And for our understanding, we'll keep it at that simple level. So again, the inside is the nucleus with the positively charged protons and the non-charged neutrons. And then circling the nucleus are the electron orbitals, or the electrons. And in this picture, we're calling them electron clouds. So it's just this kind of cloud of these orbiting electrons. But there is a rhyme or reason to how they sort of place themselves outside of the nucleus. Let me draw a picture of this. Let's say that we are, hold on. Let me find my whiteboard, it just disappeared on me. Okay. Okay, I think I need to do something. Here we go. Where's my whiteboard? Technical difficulties, just a minute. Okay, let me stop sharing for a second. Let's try it again. There's my whiteboard. Okay. I learned last year that if I maximize my screen, then some of you guys can't see where I'm drawing. So we'll keep it just at this size. All right, so we're drawing a picture of an electron, or I'm sorry, of an atom. Let's draw a picture of an oxygen atom. If you were to look at the periodic table of elements, let's go back to that. So if you go back to this periodic table of elements, you'll find oxygen here, and there's a number on top of oxygen. It says 8. It also is in column number 6 or group number 6, but we're not going to focus on that quite yet. Let's just look at oxygen, the element, and a single oxygen atom has the number 8, which signifies how many protons and how many electrons it has. There's also a number on the bottom that says 16. This is the molecular weight of that element, but we're going to focus on the number 8, which is the number of electrons and the number of protons that thing has. All right, again. So if we're focused on the oxygen atom has 8 electrons. Now, for all atoms, they follow the same kind of pattern. Here's the nucleus on the inside. Okay, the nucleus has positively charged protons and neutrally charged neutrons. And then outside the nucleus, there are these different electron orbitals. Now, the first orbital here can carry up to 2 electrons. 2 electrons in the first orbital. Oxygen has 8, so we know that 2 of those electrons will go here in the first electron orbital around the nucleus. The next orbital and all subsequent, actually not entirely true, but for our understanding, we'll keep it at that. The next orbital and all subsequent orbitals can contain up to 8 electrons. So we know the oxygen has 8 altogether. We've already placed 2 of them here. So we have 6 left over. So we'll draw these guys out. 1, 2, 3, 4, 5, 6. So we're actually missing 2 electrons. So these guys need 2 electrons to be, you can just say, be balanced. So oxygen really doesn't like to exist all by itself as a single atom. In fact, it doesn't. Oxygen exists as an atom, as a molecular oxygen, which is 2 oxygen atoms that are grouped together, or as water, or as any numerous types of compounds, right? So let's draw a picture of what water looks like. First, let's draw hydrogen. Hydrogen atom. If we go back to our periodic table of elements, hydrogen is way up here, it's an H, and you can see this is the element that we know that with the lowest atomic number, with the lowest atomic mass here, so it only has 1 electron and 1 proton. So 1 electron. So if you were to draw it again, here's the nucleus on the inside. And then this guy, because we know the rule of orbitals, right? The inner orbital can contain 2. This only has 1 electron. That's it. That's what hydrogen will have, right? It looks like this. And again, it's not balanced, right? So it's missing 1 electron. So when atoms get together, there are different ways that they can get together. One of the ways that atoms can get together is to form a covalent bond. A covalent bond is one in which atoms get together and they share, they kind of become part of one another, and they share their electrons in their outer orbital to essentially become a complete and balanced molecule. So one example of a covalent bond is H2O, or water. And this is when 2 of these guys bind to 1 of these guys. Now remember that oxygen is essentially missing 2 electrons. So it's gonna need to get those from someone. It can take them away, or more likely it's just going to share 2 electrons with something else, right? So these guys, they have a single electron, each hydrogen atom, and instead of donating them away, because they would strip themselves of electrons, they would cease to exist essentially, and we would have an atomic bomb. So instead of getting rid of the electron, which it really can't do, this hydrogen atom can come and share its electron and receive a shared electron from something else to kind of become one with a new atom. It's very spiritual, right? So here, let's draw a picture of what that actually looks like. I'm going to make my screen a little bit bigger. Hopefully it'll still work for you guys. All right, so for this covalent bond, here again is our oxygen. Oxygen atom. That's the nucleus, sorry. Nucleus for oxygen. Here again, let's just draw. It already has 2 electrons here in its first orbital. Here is its second orbital. We already know it has 6. 1, 2, 3, 4. And this time, I'll kind of draw it like this. Right, 1, 2, 3, 4, 5, 6. So it has 6 electrons. It needs 2 more. Now here come those incoming hydrogen atoms. So let's put 1 hydrogen atom here and 1 hydrogen atom here with its electron, right? These are electrons from hydrogen. And these guys are going to come in essentially and just bring in their, and this is hydrogen. That's the nucleus of hydrogen. Not the best on this thing. Okay. And another hydrogen over here. That's the electrons, and it's going to share one with oxygen. Here's the nucleus. So here's hydrogen's electron, this one, and here's hydrogen's electron. And it's going to kind of share one of oxygen. So this is an electron from oxygen. This is an electron from oxygen. Now note that the hydrogen atom has just shared and kind of borrowed electrons with oxygen. So now this guy has 2 electrons in its outer orbital, so it's rather happy. Same here, this hydrogen atom now has 2 electrons in its outer orbital, so it's kind of happy. Here's oxygen. Here's 1, 2, 3, 4, 5, 6, 7, 8. So now oxygen has 8 electrons in its outer orbital, and it's pretty happy. Okay. So what I was talking about before, the polarity of water, you can kind of see it here, right? All of these electrons are negatively charged. Negative, 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 negative. And the nucleus is positively charged. That's where our protons are. There's positive here, positive here. So note that when these electrons become shared, hydrogen, right? The electrons all shift up here towards one end of this hydrogen atom. And what's left down at the bottom regions, so to speak, is sort of the exposed proton core, the nucleus. Same thing here. So roughly speaking, and with oxygen, you can see these negatively charged electrons are all kind of up here, and its positively charged core is really hidden in the middle. So it does not have exposure of that positively charged core really all that much. So this kind of creates this roughly positively charged region here and a roughly negatively charged region here. And so this is what creates what we call the polarity, a polar molecule, or the polarity of water, right? That water creates this sort of positively charged region here and negatively charged region here, which is why when you go back to that picture of looking at those water molecules together, you'll see that water sort of aligns itself with other water molecules so that the positively charged region of this molecule aligns with the negatively charged region of this molecule sort of aligns with the positively charged regions of other water molecules, and they form that interaction. This also becomes really important as we discuss some of the characteristics of water, especially how it's a really great solvent, which means it can dissolve just about anything on this planet. And it really has to do with this polarity. So let's kind of go back and look at this. Okay, so again, we're talking about atoms and sort of how they look, how they arrange themselves. An atom is the smallest unit of an element that still exhibits the properties of that element. Properties means like characteristics, like how it behaves, right? And again, this is sort of how it looks. We can count this up. 2 electrons on an inner orbital. There's 1, 2, 3, 4, 5, and 6. Which atom are we looking at here? We just actually did this as an example. This is oxygen. So you can count up how many electrons there are on the outside. There's 8 in this one. 1, 2, 3, 4, 5, 6, 7, 8. And go back to your periodic table of element to figure out which atom you're actually looking at, or which element which atom of which element you are looking at. In this case, it's water, or it's oxygen. So to, again, clarify atoms versus elements, the element is sort of, you're describing the characteristics of this thing. Gold is an element, helium is an element, carbon is an element. And then to understand the difference between when we're talking about an element versus an atom is a single unit of an element. So a gold nugget is made of gold atoms, right? The units of the element gold combine together to form a gold nugget, right? So gold atoms come together to form a gold nugget. Helium atoms come together to form the kind of gas that you put inside those helium-filled balloons. So balloons are filled with helium atoms. And if you were to look at the characteristics of those atoms, you would find that they're described by helium. These are helium elements. Carbon is an element, and when a bunch of carbon atoms get together, then they can form a lot of different things, but pure carbon would be diamonds or graphite, would be made up of those carbon atoms. And then as mentioned before, when atoms get together either with the same atom, or I'm sorry, atoms get together with the same element or of different elements, now we're talking about molecules, right? So molecule is combination of multiple atoms, and water is a great example. Okay, let's, just a second. I'll go ahead and play this one with you guys here. Hopefully you'll be able to hear it.
Most atoms don't ride solo. Instead, they bond with other atoms. Now, bonds can form between atoms of the same element or atoms of different elements. You've probably imagined bonding as a tug of war. If one atom is really strong, it can pull one or more electrons off another atom. Then you end up with one negatively charged ion and one positively charged ion. And the attraction between these opposite charges is called an ionic bond. This is the kind of sharing where you just give away your toy to someone else and then never get it back. Table salt, sodium chloride, is held together by ionic bonds. Every atom of sodium gives up one electron to every atom of chlorine. Ions are formed, and those ions arrange themselves in a 3D grid called a lattice, in which every sodium ion is bonded to 6 chloride ions, and every chloride ion is bonded to 6 sodium ions. The chlorine atoms never give the sodium atoms their electrons back. Now, these transactions aren't always so cut and dried. If one atom doesn't completely overwhelm the other, they can actually share each other's electrons. This is like a potluck, where you and a friend each bring a dish, and then both of you share both dishes. Each atom is attracted to the shared electrons in between them, and this attraction is called a covalent bond. The proteins and DNA in our bodies, for example, are held together largely by these covalent bonds. Some atoms can covalently bond with just one other atom, others with many more. The number of other atoms one atom can bond with depends on how its electrons are arranged. So, how are electrons arranged? Every atom of a pure, unbonded element is electrically neutral because it contains the same number of protons in the nucleus as it does electrons around the nucleus. And not all of those electrons are available for bonding. Only the outermost electrons, the ones in orbitals furthest from the nucleus, the ones with the most energy, only those participate in bonding. By the way, this applies to ionic bonding too. Remember sodium chloride? Well, the electron that sodium loses is the one furthest from its nucleus. And the orbital that electron occupies when it goes over to chlorine is also the one furthest from its nucleus. But back to covalent bonding. Carbon has 4 electrons that are free to bond. Nitrogen has 3, oxygen 2. So carbon is likely to form 4 bonds, nitrogen 3 and oxygen 2. Hydrogen only has 1 electron, so it can only form 1 bond. In some special cases, atoms can form more bonds than you'd expect, but they better have a really good reason to do so, or things tend to fly apart. Groups of atoms that share electrons covalently with each other are called molecules. They can be small. For example, every molecule of oxygen gas is made up of just 2 oxygen atoms bonded to each other. Or they can be really, really big. Human chromosome 13 is just 2 molecules, but each one has over 37 billion atoms. And this neighborhood, this city of atoms, is held together by the humble chemical bond.
Awesome. I'll let you guys watch through the crash course on water. These are really excellent videos, but we're not gonna, I'm not gonna put this on right now, but it is good at showing you characteristics of water. Okay. Oops. There we go. Okay, so some of the characteristics or the properties of water and why this is such an essential part of all living things, right? Water is cohesive and adhesive, so it sticks together and it sticks to other things very well. Now this is super cool. If we were in class, I could show you a really neat experiment to show the capillary action of water. In fact, if you have ever wondered how a giant tree, think about like the biggest tree you've ever seen, like a giant sequoia or redwood. I'm gonna sneeze, hold on. Excuse me. Have you ever thought about how these trees get water? Where does that water come from? Every living thing needs it, right? And you might imagine that maybe some water comes from the sky and sort of lands on the plant and gets absorbed. No, some water can do that, but most of the water in a tree comes from the ground. So how does water go from the ground all the way up against gravity up to the tops of the trees? It's kind of a crazy concept. Well, it has to do with this cohesive nature of water, surprisingly. So as mentioned already, water likes to polarize, right? So there's kind of a positive and negative charge to each water molecule. And because of this, and because there's many water molecules that are kind of together, they form these things called hydrogen bonds. This is the third type of bond. So actually you've heard of all three of them now. You've heard of covalent bonds that you see right here, that electrons are shared between different atoms. And it's a very tight bond. We've heard of ionic bonds, which we'll look at in just a minute, where you have ions that are created by the actual taking and giving of electrons from those outer orbitals. And those molecules, those ions then associate next to each other. So it's an ionic bond. And the third type of bond that we know of is this hydrogen bond, which is a very loose bond. But it's one that can keep things organized very well and keep things associated with each other. So these hydrogen bonds will allow this kind of stacking of water molecules next to each other, or sometimes even on top of each other. And so when I think of what's happening inside of a tree, I'm gonna try not to say oops. Oh, I forget. So when I do this, I think I have to go out of the, there we go. Okay. I'm going to erase this whole thing. I'm going to draw you a tree, and you can see my wonderful drawing skills. So if you think about a tree, right, and it has this, this trunk, and then in the trunk there's all these roots, and they're trying to get water and actually bring it up. So I should not draw it that way, I should draw it that way. Water needs to go from the ground up the tree all the way up into all of these leaves. Whoops. Jeez. All of these leaves that are out here. Yes, I'm a horrible artist, especially on my whiteboard. All right, so water somehow needs to travel upwards. How does it do that? Well, I like to think of it as like each water molecule is a little person, right? Bear with me here. Here's a person, and it's holding on to another person. If you guys have ever done this when you were a kid, where you like make these little cutouts, right? And it's a bunch of people that are kind of holding on to each other. So here's a water molecule, and it's kind of polarized and it's grabbing another water molecule. And as water, like it's the opposite of being sucked up. So here, let's put the first water molecule up here in the leaf. Let me draw it a different color. Let's draw water blue. So here's a water molecule up here. Now, what do we know about what happens when water gets to the end of a tree or a leaf? Well, it actually it transpires. So it goes out into water vapor, right? So water from the tip of a tree gets sort of pulled out of the tree through transpiration. where it turns from a liquid form into a gaseous form, but it's still a water molecule, and it still has some association out here in the gaseous form as it does in the liquid form. So here's water getting transpired or kind of getting drawn out of this leaf into the atmosphere. Now, as that water molecule leaves, remember, I just told you that water likes to polarize and sort of bind to each other. Each of these guys is like a water molecule. And each of these bonds here is a hydrogen bond. And water is actually forming like this long chain all the way up through the capillary network of this tree, all the way up to each of the leaves. So if you just kind of picture that water, and I'll just sort of draw this as a long snaking thing, goes up through like the veins of a tree, all the way up through the branches, all the way out to each of these leaves. And even in the leaves, you can look and see the veins in a leaf. And water follows this whole pattern. It's not disconnected. It's all kind of connected together through these hydrogen bonds. And so as water transpires or leaves this leaf, it essentially draws all the water molecules up the branch, right? So here's our little network of fellas. And they're all sort of bonded together here. And so as this guy gets taken out through transpiration, it's like how a tree exhales, right? So this guy is pulled out this way, then it's gonna actually pull the whole thing upwards, this whole chain of molecules upwards. And so that's kind of how water moves up and supplies the needed resources to all the different parts of these plants. And not the same in humans, but definitely true for plants, right? This process of transpiration. So this is all about the cohesion of water. If water weren't coherent, if it didn't cohere together, then you would not have the ability to grow these massive trees, because water, it just wouldn't travel upwards, right? If it didn't adhere together, then you wouldn't have this capillary action, and you therefore would not have the ability to create these beautiful things that we have out there. All right, so that's this concept of cohesion and adhesive properties of water. It kind of sticks things together and allows us to grow really big trees. Water also, as mentioned before, is an excellent solvent. That means it can dissolve things. Now, we all know that if you put salt or sugar in water and mix it up, then that salt or sugar goes away, right? Salt is an ionic bonded molecule, as you just saw in that video. So these sodium chloride molecules are actually just an association of a positively charged sodium ion and a negatively charged chlorine ion. And they associate together, they associate together in this large salt crystal. But when you put this salt crystal into water, what happens is that water, essentially those molecules of water, zoom into that salt crystal and disassociate it, right? So instead of the sodium and the chloride associating together, remember the water is polar. So it also has a positive and a negative charged region. And so what you'll find is that in a solution of water, the polarization of water actually creates these little water, I don't know what you call them, but these associations of water molecules and each of these ions that are in there. So this is true of any polar substance that you put into water. So anything that you put into water that has the ability to polarize, either naturally because they're ions like sodium and chloride, or because they have atoms in it that do polarize as well. So for example, sugar is not an ion. It's 6 carbons and 12 hydrogens and 6 oxygens. But because it has those types of atoms in there, those atoms can polarize and associate with water very, very similarly, as we talked about before. In this case, you'll see that the positively charged sodium ions will associate with the negatively charged regions of a water molecule, the oxygen end of a water molecule. The negatively charged chlorine ion will associate with the positively charged polar end of the water molecule, or the hydrogen regions of the water molecule. And so this lattice of that salt crystal, that molecule, will be disassociated and or dissolved, right, by water, essentially those molecules like wrapping themselves around each individual ion here. So water does this very, very well and very, very rapidly. Sometimes it takes a long time. If you put a piece of metal in water, of course, that's a very slow process, but water also will dissolve metal, right? It's called corrosion, but it does happen, a slow process sometimes. So more properties of water helps make many chemical reactions take place. So water provides sometimes that needed combination. So the liquidness of water sometimes can help cause reactivity. Usually it's the positively charged region or the negatively charged region of that polar molecule that can help stimulate a chemical reaction. In fact, most chemical reactions do not take place without without water or some type of liquid substance, but water is the foundational kind of component here that makes most things work. In biochemistry, so looking at chemistry inside the cell, this is absolutely true, that without water, very few chemical reactions would ever take place because they require that aqueous environment and the association of that polar molecule to make these reactions work. So when you dehydrate a cell, when you take out the water, which happens when you eat a bunch of potato chips or eat a very salty or a very sugary meal, then actually you're pulling the water out of your cells, which is why you get super thirsty, because you need to rehydrate your cells. But when you're taking the water out of your cells, then you actually reduce their ability to create chemical reactions, which stops your metabolism altogether. And that's what happens when you dehydrate, that you just can't have chemical reactions happening in your cells, which shuts down your cellular processes, which shuts down your organs, which then shuts down your whole body. Here's another property. We know that frozen water will float. If you guys didn't know this, then you can go experiment right now in your freezer. Go freeze a cup of water and freeze it for a half hour and see what happens, or freeze it for an hour. You'll see that the frozen part goes to the top and the non-frozen stuff goes to the bottom. Now this is unusual and incredibly unique. Everything else on our planet that we know of that is not made mostly of water, when it freezes, it is heavier, right? And if you think about it, a frozen state of matter means that, or a solid state of matter means that the atoms are more densely packed. And when you create a more densely packed molecule, then that, a more densely packed substance, then that becomes heavier. It's more molecular mass in a smaller place. And so those solid things usually are heavier than their liquid form and definitely heavier than their gaseous form. Water is different, right? So the solid state of matter, the solid state of water is ice, and ice is actually less dense than the liquid state of water. And this allows for our oceans and our lakes to get really cold, to freeze, and not kill everything that's living in there, because the ice will rise to the top instead of staying in the bottom and freezing all of the living organisms that are down there. So it's a really, really crazy thing. If you want to get into the chemistry behind this, there's a whole stuff that you can watch on how frozen water is, floats and doesn't sink like everything else that's in solid state does. Water absorbs and holds heat well, so this becomes incredibly important when we're talking about homeostasis, or the ability to regulate internal temperatures. This is also important when we're talking about every other life form, not just in humans, but even bacteria. This concept of water being required for heat transfer is one of the ways actually that bacteria can exist for maybe tens of or hundreds of thousands of years in something called the spore form. So bacterial spores can form in harsh environments where they essentially take advantage of this concept of water, and they dehydrate their central core and create a really tough capsule around their DNA. And that way they actually are resistant to heat. Like, heat doesn't affect a spore unless it's extremely high temperatures. Because there's no water in the inside of these spores, and so there's no transference of heat when there's no water. Kind of crazy. All right, so this is going to continue this concept of looking at chemistry, but now moving sort of away from water, looking more at acids and bases. And it still has to do with these basic atoms of oxygen and hydrogen, but now how they can associate or disassociate with each other and create positive and negatively charged solutions. And that's what we're referring to as acids and bases. Let's see how long this video is. All right, let's do this one.
When water dissociates, it breaks apart into an equal number of hydrogen ions and hydroxide ions. In contrast, when other substances dissociate, they may release more hydrogen ions or more hydroxide ions. For example, hydrochloric acid releases more hydrogen ions as it dissociates, and sodium hydroxide releases more hydroxide ions. Depending on its concentration of hydrogen ions versus hydroxide ions, a substance can be classified as either an acid or a base. The pH scale measures how acidic or how basic a substance is. It ranges from 0 to 14, with 7 being neutral. When a substance has a pH of 7, like water does, it releases an equal concentration of hydrogen and hydroxide ions. When a substance has a pH of greater than 7, it's classified as a base and releases a greater concentration of hydroxide ions. The more hydroxide ions that are released, the more basic the substance is. Bases tend to feel slippery and are often used as household cleaners. Milk of magnesia and ammonia are both common bases. When a substance has a pH of less than 7, it's classified as an acid and releases a greater concentration of hydrogen ions. The more hydrogen ions that are released, the more acidic the substance. Acids tend to taste sour. Lemon juice, stomach acid, and coffee are all examples of acids.
All right. Okay, so that's our pH scale. I think that video is a good descriptor of how we, what defines our pHs, our pH scale. Again, neutral does not mean that there are no charged ions in that solution. It means that there's an equal amount of positive and negatively charged ions in that solution. Pure water, water H2O does have some dissociation. So there's kind of this always, actually everything in biology and almost everything in chemistry is never in stasis, is never kind of a standstill. It's always kind of fluctuating. So water is no exception to that rule. There's always a dissociation, a loose dissociation between pure H2O and a hydroxy ion, which is OH negative, or hydrogen protons, which is H positive, right? But there's an equal balance at neutral pH, at pH of 7. There are a few things in nature. Water obviously is one example of a neutrally charged substance. Our bodies actually are not neutrally charged. We have a slightly alkalinic blood inside of us, even though we're made mostly of water, but the other substances we have create a slightly different charge to us. Even though it says blood here, we are still within the neutral range, but we are slightly alkalinic. Acidic solutions have more hydrogen protons, or more positively charged, dissociated positively charged ions in that solution. And this can form when you add something to water that continues that dissociation, where there's more protons that are released. Stomach acid is really, really low. We can have pH down of 2, right? So here's the pH scale. So 7, essentially anything below 7 down to 0 would be acidic. And the lower you get on the scale, the more acidic it becomes. And the more acidic something is, the more reactive it is too. So these things that are way down here, battery acid would be down at pH of 0. Orange juice and even soda is like pH of 3. Your stomach is around pH of 2. If you're a baby, your stomach acid is closer to pH of 5 or 6. Coffee is even slightly acidic, right? So some people have reactions to coffee when they drink it regularly because it does have that acidity to it. These things all can be somewhat reactive, but the more close you get to 0, the more highly reactive, which means if you put this battery acid, for example, on your skin or an organic compound, it will cause a massive creation, or disruption in the molecular structure of the molecules that are in your hand, and that's how we have this high reactivity. Same thing with basic solutions, but the opposite end. For basic solutions, we have things that have more negatively charged hydroxy ions than the positively charged protons. Baking soda is up here on this category, ammonia, and the up high at the very, very top is that Drano, or liquid drain cleaner, right? Which if you ever have used this before or have read the bottle, there's massive warning signs all over it, like don't let this touch anything, don't even let it touch their drain because it's highly corrosive. So anything that has a very strong basic charge is highly corrosive. That kind of means the same thing. It becomes super reactive and will try to find a way to neutralize its charge by stealing protons from anything that it's around, right? So these scales, and if you kind of think about acid bases, you know probably from even just your own experience, acids and bases can neutralize each other, but also can create quite a voluminous reaction when they first get together. But if you needed to neutralize something that, for example, you have an acid burn on your hand, then you don't use water because that will further exacerbate it. You actually need to go with something that's more basic to neutralize that solution. Fun adventures to do with your children or even with yourself is to find these just slightly acidic and slightly basic components and combine them together, and you can see that highly reactive nature of when an acid and a base get together. But the end result is always a neutral, well, as long as you're getting a well-balanced acid and base, the end result of that combination is usually a neutral substance. So the classic example is baking soda and vinegar. If you put these two things together, you'll get that volcano that all kids do their science experiments about in 4th grade or something. That's because vinegar is slightly acidic and baking soda is slightly basic. And when they get together, they have a really nice reaction, resulting in a neutrally charged solution at the end. All right, this last section here is just looking at biochemistry, in fact. This is looking at the 4 basic types of organic molecule that make up the foundation of just about everything we see on our planet. So this is actually a really cool concept if you think about it. Every living thing that you see with your eyes, everything that we are made of, like head to toe, including all the viruses and bacteria and protists and fungi that exist inside and on our skin, everything that we breathe that is alive, every living thing shares these 4 foundational, we call them macromolecules, and they're carbohydrates, proteins, lipids, and nucleic acid. Now I'm going to do a quick screen share. We're going to make a little table. Let's see what this is. Oh. All right. We'll just draw this real quick. Okay, so we're going to make a quick table of what these macromolecules are. And then over here, we'll say what it's made of. What is its individual unit? What is its monomer? Let me explain what that means just a second. And then we'll do, monomer. Example. Okay, so the first macromolecule we have on our list is a carbohydrate. If you guys don't know what this is, a carbohydrate is sugar, right? So carbohydrates are your sugar molecules. Carbohydrates, proteins, lipids, and nucleic acid. Let's just add those to our list here. And we'll go through the slides and sort of add to this whole thing. Come back here. Oh, here we go. We can't add to what I was already drawing. Interesting. Carbohydrates, proteins, lipids, and nucleic acid. So those are the 4 macromolecules we have that make up really every living thing. could open up a different file and share it a little bit easier. The macromolecules, carbohydrates, proteins, lipids, and nucleic acid. Let's figure out what each of these things are made up of, right? So when we're talking about monomers versus polymers, this term mer kind of means individual unit, right? So when we're looking at this term mer, it means like unit. And so to understand these different terms, mono, how many individual units would mono be? 1, right? 1 individual unit. And poly, means many, right? So let's put these terms together. If mer means unit, right, individual unit, monomer means 1 unit, polymer means many units put together. So these macromolecules, and we call them macro because they're very large, right? Macro means very, very large. So these very large molecules are essentially repeated units, repeated monomers over and over and over again to form these very complex, very large macromolecules, these very large polymers or very large structures. So let's go back to our slides and understand what each of these things are. So first, carbohydrates. Again, these are sugars. We call them sugars here. So we have these different ways that sugars can combine themselves together. Sugars are really, really important for all living things. Almost all of our structural components are made up of sugars. For bacteria, their entire cell envelope, their entire cell wall is made of sugars. Same thing for plants. All biomass is basically sugar, and it's just combined together in these very different types of linkages of these sugar molecules. So an individual unit or a monomer of a carbohydrate, we will actually call it a saccharide. So look at these terms here. This is a super simple glucose. Glucose is like a foundational carbohydrate that's used for energy for almost every living organism. So we take this glucose molecule, put it inside of our cells, and our cells start to break apart this glucose molecule and release energy every time one of those carbons are snapped off of this little structure here. We'll look at this in a lot more detail when we talk about aerobic respiration and fermentation, because it all has to do with this glucose molecule here. Glucose is pretty complex. There's 6 carbons, 12 hydrogens, 6 oxygens to it. Other types of monomeric or monomer carbohydrates, so individual units that are carbohydrates, or monosaccharides is what we call them. There are other types of these things that are of different forms, and the body can do different things with them as well and put them together in different linkages. Fructose is another example. This is a different structure. You can see this is a pentameric, so 5 here instead of 6 that make up, or it's a 5-membered ring instead of a 6-membered ring that we see with glucose. These guys can link together in this particular linkage to form a disaccharide. Di means 2, and saccharide again means sugar. So this glucose plus fructose makes that really common table. That's actually what you see here. That's the table sugar, stuff that you use in your baking. That usually is a very common food additive is sucrose. And this particular combination works well with our taste buds, makes things taste a lot sweeter than regular glucose does. When you string together a whole bunch of these individual units in a very particular arrangement with their bonds, you can create these polysaccharides. Poly again means many. And this is an example where glucose is put together over and over and over and over and over again to form biomass that we see with our naked eye with the trees. This is cellulose. So all plants are made up of just gigantic strings of polysaccharides, many glucose molecules that are strung together to form these big biomass things. So let's add this to our list here. So for carbohydrate, our monomer that we have, and actually I'm just going to draw this so I can draw it in the right spot. For carbohydrate, the monomer, we're going to call it a saccharide, or a monosaccharide. A good example of this one is glucose. right? When these molecules get together, we can form a di or polysaccharide. And an example of a disaccharide would be something like sucrose or even lactose that's in your milk. Polysaccharide would be like plant biomass, which is cellulose. An example of carbohydrates altogether, I've just given you 2 examples here, but even like starch, right? Starch is a good example. Any kind of sugar, like table sugar. And then for biological processes, I'll say our plant cell walls are made up of carbohydrates. So carbohydrates are really important in structural features in the world, but also in energy. So actually starch and sugar are used as forms of energy. So hopefully you can see the function of carbohydrates is important for both structure and energy. So as a source of energy and also a source of structural components for different things. So carbohydrates are polymers of individual monosaccharides, right? They can be disaccharides, polysaccharides. They can be of the same sugar repeated over and over, or multiple sugars repeated in different linkages, and they give lots of complexity to our living things. Almost done here. There you go. So the 2 major functions of carbohydrates are to provide energy for living things and to provide structure or structural support. And this was the example I just gave you. Cellulose makes up plant cell walls. Something called peptidoglycan makes up bacterial cell walls. All of those things are types of sugar molecules. And then for energy, sugars are used to make energy, right? In almost every single living thing. There are other energy sources we have, like lipids. We can make energy out of fats, or proteins. We can make energy out of there. But our cells are designed essentially to first and foremost attain their energy through sugars. If you have sugar in your cell will use that sugar first. That energy is stored in the form of starch in plants or glycogen in animals. So for us, we take in sugar with our meal. Our body takes that sugar and sends it throughout the blood. Our cells absorb it with the help of insulin. You guys have heard of this before. And that sugar, some of it is immediately used for energy, but whatever is not used right away is stored away as glycogen. It's a pretty cool process. All right, here's these terms I've just given you: polymer versus monomer, right? Again, mer is that individual unit. So when many monomers get together, they form these polymers. What we just talked about here, these polysaccharides are polymers of monosaccharides, or those simple sugars, what we just wrote out there. Just get used to these terms. This is a picture of that polysaccharide that's used to make the biomass in plants, right? So here's a picture of what that starch might look like, or the cellulose that makes up the cell walls of plants there. Glycogen granules, you'll see here, this is, as just mentioned, what we do within our cells. We take in glucose, and then whatever's not used immediately, we store away as glycogen. And then when we are starving or between meals, we have a way to slowly release the glucose from our glycogen storage inside of our cells. Okay, next on the list is proteins. Protein is another example of a macromolecule. It's made up of individual units. In this case, the units that make up proteins are amino acids. So a single part of a protein is an amino acid, and amino acids get together with other amino acids to form polypeptides, or chains of amino acids. And these things are then folded in really unique ways, bonded together to form an entire protein structure. The function of proteins is to provide structural support. So we know in humans, most of our muscle mass is made up of proteins. But proteins are really, really important in biological processes too. In fact, in my classes, I usually focus way more on talking about proteins as essential for metabolism, because enzymes are proteins. Enzymes are proteins that are biologically active, right? So they do stuff, and they help allow all biological processes within the cell to actually work. Inside the cells, and between, especially in eukaryotic cells, between organelles, between these different functional units inside a cell, proteins are essential for transport, bringing a molecule or an enzyme or a vacuole or whatever it is from one place in the cell to another to transport things into the cell or out of the cell. And then also, like as in a larger picture, in the functional processes of a human body or of an animal body, so in muscle contraction, for example. So there's a lot of functions of proteins: structure and transport, movement, and as enzymes are some of the things that are listed here. Okay, let's draw those things out in our whiteboard. So again, we're sort of looking at all of these different things. We just drew out carbohydrates, and we understand the individual unit of a carbohydrate is a saccharide or a monosaccharide. For proteins, it's different. So proteins are made up of amino acids. Let me just draw a different color because my graph is a little small here. For proteins, we have our individual units are amino acids. And your book will go into a little bit more detail on what these amino acids look like. These guys are called peptides. So an amino acid is also called a peptide. And so therefore, when you link a bunch of peptides together, we call it a polypeptide. And we'll discuss how polypeptides are made during our chapter on genetics when we look at transcription and translation, because that is the process where DNA is read by cellular machinery, and there's code that instructs translational machinery to put together very specific peptides in an order and form bonds. We call them peptide bonds between these amino acids to form this polypeptide that then can be folded and turned into a protein, right? So examples of proteins, a great example would be your muscles, but I'm even just going to say enzymes. And these guys are biologically active. We'll talk about enzymes a lot more in our chapter on metabolism. All right, lipids is next. We're almost done. Whoops. So lipids is the third category of macromolecules. Now, a lipid is otherwise known as fat, right? Fats are what we call these things. There's a picture of lots of fat that is smothered all over these cheese fries here. So in this picture, what are the lipids? Well, cheese has a lot of fat in it. It actually has a lot of carbohydrates in it too, right? So there's another macromolecule in there. In fact, cheese is made up of a lot of lactose. And there's grease that was used to fry these potatoes. So the grease is another form of lipid, right? It's oils, and oils have a slightly different property than the lipids that you'd find in cheeses, but very similar in its basic molecular composure. And then we also have the potatoes in this picture too, and the potatoes have tons of carbohydrates, tons of starches in there. So we have two different types of macromolecules that we're looking at, carbohydrates and lipids in this picture. So lipids are made up of, actually there's a few different forms of lipids or fats, right? The purpose of these is energy production and storage. So lipids are really, really important inside the body, inside a cell. Even if we're looking at a single-celled organism like bacteria or protists, lipids are vital for energy storage. So in the membrane of every single cell, we have lipids. That's what actually our membranes are made up of. And those membrane lipids can actually be used for energy. They can be taken out and used for energy production instead of just as structural support for our cells. An example that you see here is a triglyceride. This is the type of fat that we use in our diet, and our bodies in the digestive process will break this apart and release the glycerol molecule and release these fatty acid tails, and those can be rearranged by our cells to be used for membrane or for energy production. So here's a picture of what a triglyceride looks like, where these fatty acid tails are down here, and they're kind of held together by this glycerol backbone. That's just sort of this head part that has these ability to bind to these three different fatty acid tails. Now, what these lipids are really made up of, we call them hydrocarbons, because that's just it. They're carbons that are linked together that are saturated with hydrogens. And if you've ever wondered what these terms saturated versus unsaturated, poly unsaturated, monounsaturated, it has to do with these hydrogen atoms that are bound to the carbon atoms in this hydrocarbon tail. So if any of these hydrogens are gone, then the carbon will form a double bond with its neighboring carbon, and that will be an unsaturated carbon, right? Right now, what you're seeing is a picture of a fully saturated hydrocarbon. That means every carbon is bound to 2 hydrogens. But if those hydrogens are gone, if they're removed, then those carbons will be unsaturated, right? And if you have 2 carbons that are unsaturated next to each other, they form this double bond. It makes that lipid a little bit more solid, right? As they're saturated, they're very, very fluid. And this is important for membrane structure for our cell membranes. We'll talk about that in more detail when we talk about metabolism. And as you get more of these hydrogens gone and the carbons like bonding really closely to each other, these unsaturated fats become a little bit, they become a little bit more rigid, right? And polyunsaturated means there's lots of these double bonds throughout this whole thing. So this would be a picture of a triglyceride where you have fatty acids here that are bound to a glycerol, but there are other types of fats as well. Oh, there you go. So here's a picture of where that double bond has been formed, and you can see it kind of forms this steric change, this change in the structure of this hydrocarbon tail, whereas this is a fully saturated and this is an unsaturated part of this fatty acid. Okay, well, so when you have saturated fatty acids where the hydrocarbons are completely bound to each other, right, then they can essentially stack really, really well. So when you bring something like this to room temperature, it will stay in a solid form. An unsaturated fat or fatty acid, they don't bond very closely together. They sort of are hard to get really close, and so they'll stay in that liquid form. So that's kind of the difference here between a solid stick of butter and an oil, is the saturation of those fatty acid tails. These are other types of lipids too. So we just saw triglyceride as one example, and that's really important in providing us energy and providing us with fatty acids to make our membranes. But especially for animals, we have cholesterol and hormones. So hormones are types of steroids, which are basically types of lipids, right? So these are not important, lipids are not just important in energy and in membrane function, but also in cellular communication or whole body communication from one body system to another. So hormones are our messaging chemicals that are secreted by our endocrine system. They're controlling like many, many different cellular activities in the body. Many different organ systems require this hormonal communication between like triggers that go up to the brain, and the brain sending different signals out to different parts of the body so that you have regulation for your different body functions. But these are all fat-based. These are all types of lipids. So cholesterol is actually one of the foundational lipids that is used to be converted into different types of hormones that then can have different cellular processes. So it's quite important to have an appropriate amount of lipids and in the right sort of composition so that your body has all of the necessary lipids to function both for energy purposes and for cellular communication process. So phospholipid is what makes up all cell membranes. This is a glycerol backbone with 2 fatty acid tails. And again, these are hydrocarbons, just like we saw before. And it kind of looks like this, and you'll see that when we look at our cellular cell structure and function in chapter 3, and also when we talk a little bit more about nutrition and metabolism, we'll talk about these guys again. So let's go and just sort of add some very simple things to our explanation of lipids here with our whiteboard. For lipids, for most of these things, many of these lipids, they're made up of fatty acids. Oops, let me draw a different color. So lipids, we're going to say most of them are made of fatty acids, which are types of hydrocarbons. And these guys can, that's buns, these guys can get together to form things like triglycerides or phospholipids, right? So we'll say the combination of these hydrocarbons together, when they link up with the other ones with that glycerol backbone, they can form something like triglycerides or phospholipids. There's actually a ton of variety of this, right? And so these things would be really important, for example, in our cell membrane. as an example. And there are lots of other examples of how these things can be really important for energy production, for structural features, for cellular communication processes, etc. Okay. So the very last type of macromolecule that makes up all living things are nucleic acids. This would be specifically deoxyribonucleic acid or ribonucleic acid, DNA, or RNA. And these are more examples of macromolecules. If you look at them up close in person, you'll see that DNA is made up of these individual units called nucleotides. There are 4 different types of nucleotides that make up all the DNA units, and 4 different nucleotides that make up the RNA units. These things have really important features that allow that really cool double-stranded, double helix structure of our DNA molecule, and gives us our unique properties that allows proteins to be made in a very consistent format, and our understanding of the genetic code. We'll talk about all this stuff in our chapter on genetics and how we understand nucleotides to work, and the sequence of nucleotides to determine the arrangement of our proteins. But for our understanding here, we just need to see this as a molecule. And this molecule has these repeated units of nucleotides over and over and over. And a couple of important things to note about nucleotides. An individual nucleotide is made of 3 different parts. It has a phosphate group, which is a phosphorus molecule surrounded by 3 oxygens. It has a sugar component, so your carbohydrate ring here. That would be either deoxyribose here for DNA or ribose for RNA. And then it has this nitrogenous base, and this is a really large nitrogen-rich unit that is where we get kind of our rule of binding for DNA and RNA. And this is where we talk about our nucleotide bases. So adenine, guanine, cytosine, and thymine are the 4 different types of nitrogenous bases that make up those nucleotide structures here for DNA. And then instead of thymine, we would have uracil for RNA. So this single nucleotide unit that you see here with the nitrogenous base, the deoxyribose sugar, and the phosphate, this is one individual nucleotide. All of these components are linked together with covalent bonds. But when you have one nucleotide that binds to a complementary nucleotide on another strand of DNA, you can see these kind of dotted lines here because the bond is very loose. This is a hydrogen bond that's formed between 2 complementary nucleotides on 2 different strands. And then on the same strand, one nucleotide is bound to its neighbor, and it doesn't matter kind of the arrangement of the bases. This is something we'll cover in genetics, but the binding of one nucleotide to the neighboring nucleotide is also covalent. So a single strand, if you were to take this winding double-stranded DNA molecule and you split it apart, a single strand is really, really rigid, bound completely covalently from one nucleotide to the other all the way down. And even within a nucleotide, those 3 different components, that phosphate, sugar, and nitrogenous base are really closely linked together. So an individual strand of DNA is formed of a really tight bond, but when that DNA strand comes together with another DNA strand, the connection between those strands is actually quite loose, and this is a covalent bond. Oh, sorry, this is a hydrogen bond that's formed between these. Okay, so let's write this down real quick on our little chart here. So our last macromolecule example is nucleic acids, and the single unit that makes up all nucleic acids are nucleotides. And remember, this has 3 different units. It has that phosphate group that's covalently bound to a carbohydrate, a sugar, that's covalently bound to a nitrogenous base. And we'll look at this in more detail when we get into that chapter on genetics. These nucleotides form together with other nucleotides to actually form nucleic acid, right, when they bind together. And then this would either be DNA or RNA, depending upon what types of nucleotides there are that are binding together. Okay. All right, this last slide is just showing you one other example of a type of nucleic acid. This is ATP, adenosine triphosphate, which is also a nucleotide, but this one is really important in producing or storing energy within a cell. So we'll talk about this in a lot more detail when we get into our chapter on metabolism and looking at aerobic and anaerobic respiration and fermentation. But for now, you can just understand this is, again, another example. In fact, this would be a monomer of nucleic acid, a single unit, a nucleotide. But in this case, it's used all by itself just for energy storage and for kind of energy production, but mostly energy storage in the cell. And we'll talk about its function downstream. All right, that's it for these slides. Hopefully this was helpful to you, and I'll catch you again later.